I was taking our knowledge of conic sections onto the next level and taking a look at, in previous questions we would have maybe seen some of the basics of cutting a cone for using maybe a vertical plane to find the hyperbola top and bottom, cutting through all set of generators or elements in the cone and getting an ellipse, or cutting parallel to one of the generators and finding a parabola. We would have already been able to find the true shape of the cut sections using auxiliary views. But now we need to just take it a step further and start looking at some more terminology to do with the topic of conic sections. So this time we're dealing with a parabola. The section is parallel to the generator. There's a lot more to add in. As you can see, it's not just about the true shape of the section cut this time, there's a lot more going in here. Just to start adding some notes on the graphic here, because that's going to be very helpful. First off, this dark plane here at the back, that is the section plane that cuts the object, so I'll just label that as section plane. That section plane is resulting in a parabolic cut or parabola. This guy right here is called the focal sphere. When the section plane cuts the cone, in the remaining space up here, we can put in a focal sphere. There is only one possible focal sphere for any given cut. The focal sphere is in contact all around the cone, and it also touches the section plane. It touches the section plane at a focal point. That's where focal points come from originally. So if the central axis of the object or of the section plane there, if we extended that right down along just to see it, along that axis we get a focal point. The focal point is the point of contact between the focal sphere and the section plane. When we take the circle of contact there, between the focal sphere and the cone. When we take a look at that circle of contact between the focal sphere and this cone that it's within, if you extend that and drop a plane in, that plane here, I just call this plane 1, that's an extended plane from this circle of contact that the sphere makes with the cone. As we extend that through, it gives us a really important line. The line of intersection between the plane and the section plane is called the directrix, D-I-R-E-C-T-R-I-X. That's some of the very important terms that we will be coming across. Now there's going to be some more, but at the moment the vertex of the given curve is just where it is, where it exits the object here, or where it changes direction, I suppose I should say. So there's one vertex in the parabola. We have the focal sphere here, the focus or the focal point, and the directrix is the line of intersection between the plane on the circle of contact extended to hit the section plane. So it's that line of intersection along there is called the directrix. I'd like to get all of that onto our 2D. So just to check the question, would you please, in your own time, just put in the explanation of the following. So explain the section plane, vertex, focal sphere, focus and directrix, just all based on what I've worked through there. The given cone is cut by a section plane resulting in a parabola curve. Find the axis, the vertex, the focus and the directrix. Okay, so find the axis, vertex, focus and directrix. The axis is this line here that goes down through the center of the section plane and through the vertex, through the focus and down through the center of the parabolic curve. We're going to take a view looking at 90 degrees to the section plane. Just labeling that guy as section plane. I'm going to take a view looking at 90 degrees to that section plane. And that's where we're going to see the true shape, and we're going to see everything that we've been asked to find. So I'll just use my adjustable here. Maybe it's set at 60 degrees. I should check that first. Yeah, it's given us 60 degrees, which makes it easier. So if I project off at 30 degrees, I'll take the bottom point, which is the ends of the legs of that parabola. I'll take the vertex of the parabola, and I can just first off drop in an axis. That's going to be just dropped in anywhere. I'm just going to have a true shape of the parabolic curve, and then all extra detail such as focus and directrix, etc., all dropped in there on the same drawing. So I'm going to work off the center line here, the width taken from plan and applied. Next, find the axis, the vertex. The vertex is here, so it goes up from the base of the curve, up to the vertex, and back down again to the base of the curve. Find the axis, the vertex, the focus. To find the focus or the focal point, I need to find the focal sphere. Now, the focal sphere, as I said, there's only one possible focal sphere for a given cone and a given section plane, and the focal sphere needs to be in contact with the cone all around, and it needs to be in contact with the section plane. So basically, if we bring it back to 2D geometry, I need a circle that touches both of those lines, and I need the same circle to touch both of those lines. So it has to be in contact with this angle and with this angle. So it's just time to bisect the angles. Bisecting the top angle will get me a vertical line, and bisecting this angle here. We'll just get this line. That should be the center point. It's never accurate to just take a compass and start drawing and try to offer it up to 3 different lines. Instead of that, take your sliding set squares right back to first year work. We get your tangent angle off one side. When we have a tangent angle, we slide down, we get a normal. Again, same thing on the right hand side. Take your tangent angle, slide down, get a normal. And finally, I have my tangent angle here for the section plane, and I go 90 degrees to get a normal. That gets me the center point and 3 points in the circumference of that focal sphere. So I can draw that in now. Just test it before you draw it in. Mine's not very accurate, so I'm just going to make it fit there. There we go, that's the focal sphere. When I have a focal sphere, I need to establish the exact point of contact. So once again, whenever you have a circle and a tangent line, you can have your normal line here, and that gives you a point of contact. That point of contact is the focal point. In green here is the focal sphere. I'm going to bring my focal point down until it's on the axis line. Next, I'm going to just have a look back to what I have here. If I can get the circle of contact, so where does the sphere actually come in contact with the cone that is given? And it comes in contact at the end of this normal here, because that's a point of contact, and at the end of this normal here. And it comes in contact all the way around the object. So in a full circle, and that's just going to look like a straight line here because we're looking at the elevation. So in this case, the circle of contact is from any of my 2 points of contact right there. There's the actual circle of contact, and then extending it to form a plane. So circle of contact, and then I'll just call that plane 1. And where plane 1 extends out through the circle of contact, extended right and left, and the key point is where it extends and hits the section plane, gives me the line called the directrix. Now, look, the importance of all these terms and all these items will become apparent in the coming days and weeks when you progress through the topic. For now, you need to be familiar with them and kind of see where they come from. In junior cert, you'd always have heard of a focal point, particularly in the ellipse questions. You're going to see in the next couple of worksheets where the ellipse focal points, 2 focal points, come from. In this case here, that's how a parabola's focal point is derived. Just here, before I go any further, that is a point view of the directrix. Point view of directrix. So the directrix is a line. I'll bring that down again. The directrix line is always at 90 degrees to the axis. We often call it DD1, and in this case I'll just drop down the full name, directrix, as well. And as I said, it's always going to be at 90 degrees to the main axis through the object. That directrix has a lot more uses and a lot more mathematical uses, I suppose, in terms of its proportional relation to all points on the curve, but we'll get back to that again. Focal point being the very same. The focal point and the directrix are very, very useful, and at a later stage you'll see why. For now, I would like to finish my question by actually drawing the curve. So find the leg of the curve up to the vertex and back down so that I can get the true shape of this parabola. To do so, I'd need to take, that's point 1 there, which is out at the front. I did say that I'm going to set the axis of the object, just like it is, down to the centre of the curve. So that's the axis right there. So I can take all points symmetrically up and down, or left to right, off that axis. So down to point 1 and up to the finishing point as well. I'll call that point 1. I won't label the other point just yet because let's see how many points along the way I get. That gets me started. That's going to be the finishing point. I need some more along the way, so I'm going to just drop in some elements here. I put them all in maybe in orange, or maybe just go 30-60 on all these. And those elements there are going from the apex 0. They're going. We have 1 already done. Then there's point 2, 3, 4, 5, 6, and then we'll call that one 7. So that is point number 7. Time to draw those straight line elements or generators. I want to draw them in the elevation going from the apex down to the ground. They're going to line up, so 2 and 6 happen to coincide there, 3 and 5 coincide, and 4 is already on the extreme edge. So I have 2,6, I have 3,5, and I have 4 on the extreme line. Here's what we do. So the element from 0 down to 4 gets cut here. The element from 0, the apex, down to 4 gets cut here, which means that is the vertex. It's a point on the graph. The remaining elements, down to 2,6 and to 3,5, get cut in their respective positions as well. So I project that guy, and I project that one. This is how we would have solved some of the earlier questions in this. Where do they get cut down in plan? Well, there's the correct width at 2 and at 6, and there's the correct width at 3 and at 5. So on the actual parabolic curve. So at 2 and 6, they get cut at this width here. That's the width out to 6, and that's the width out to 2. I'm going to follow those key points up to where they're cut and down. So I have the width out to 2 on the lower side, 6 on the upper side. Similar to that, where do these guys get cut? So I'm just trying to plot out various points in the curve. 5 gets cut here, and 3. Where are they? Up here. That's where 3 and 5 get cut. Bring them down. Out to 3 on the lower side, 5 on the upper. So I have 1, 2, 3, 4 is the vertex, 5, 6, 7. I don't think there's quite enough points. For myself, for freehanding this in, I'd like 2 more points here. So a different method and a different, and probably a simpler approach even, is just take any point at all and project. And because we have the curve given to us in plan, usually we don't have the curve in plan. I'm so used to doing this where we don't have the curve, maybe we have the curve in elevation and we have to draw the elements and find the cut points and project, but it's all given. So if I just take that as a point in the elevation, bring it down to hit the curve in plan, I can now take, it's got a little bit heavier so it can be seen on camera, I can take the width out to this point on the curve and back to this point in the curve, and that's going to plot along this line. It's just that the extra points now are quite useful before I start freehanding. So that's how we do it. For a question like this, I didn't necessarily need the elements. That's how you'd solve it if you were just given if you were given the cut in one view or in the other only. If I was just given the cut here, I'd use my elements, bring the elements back down, draw them, and bring the points where the elements get cut down to hit. So I didn't necessarily need them this time, but nevertheless, it has worked. Time to freehand this in. And there we go, we get a true shape of the parabola. So true shape of the parabola. Have I managed to answer every single part of the question? Find the axis, vertex, focus and directrix. So we have the axis, the vertex, the focus, which came from this point here, and the directrix, which came from the extended plane intersecting the section plane. Label the pictorial and orthographic drawing using the following terms. The section plane we've done and done. The vertex is here, just right there, and it's very hard to see the vertex over here. It's just right there at the top of the curve. The focal sphere I've labelled just here. The focal point F is just there. Horizontal cutting plane, or as I call it, plane 1, horizontal cutting plane, and the directrix. Finally, point view of the directrix, and we have the full directrix right here. We never really need to add much in plan. Maybe they'll ask us where is the focal point in plan. If you were asked to do something like that, you'd realise that the focal point lies on the axis of the object. So the focal point is there. Maybe you'll be asked to do something like that. But again, if you understand it, If you understand that it lies on the axis and remember that, you have no problem projecting between views. The final part on this page here just involves labeling the little diagram. So it's basically taking this two-dimensional diagram here, which is a representation of the section views and all of the derivations we have here brought onto 2D, bringing them down here and adding a few more little pieces of terminology. Label and draw where required the following on the conic. So the vertex, easy one to start. The vertex being up there at the top of the object, so vertex. Right there. The directrix. Or, as I said before, D1. Just a label they can often give that as well. The focus is right here. I'm just going to call that point F for focus. So vertex, directrix, focus, the axis. I'll change up colors now because there'll be a lot more going in here. The axis is right there, and the axis is always at 90 degrees to the directrix. A chord, very similar to a circle. A chord is just any line that passes, touches 2 points. Is a chord. A focal chord, slight difference here, any line touching 2 points in the curve through the focal point. An ordinate is a line that goes perpendicular to the axis and touches a point in the curve. Is an ordinate. Next is a double ordinate. So you can probably guess what this one's going to be. Perpendicular to the axis, both sides of the axis. And finally, lattice rectum. That is a really important line actually in terms of conic sections, and it is the double ordinate that passes through the focal point. So there's a lot dropped in there now. And they all have their own uses and purposes. The really important ones here, I suppose, would be usually ordinates and lattice rectum being the most important lines on the drawing. But everything here has some use, and there are some theories or some parts of questions that can be solved using chords and bisecting chords and so on. A little bit like what we would have done before at a very early stage on circles. Right there, that line is called the lattice rectum, L-A-T-U-S, lattice rectum. Now, I'm not going to be writing any other notes explaining them. I just want you at the moment to understand what they are. The only little note I'll add here is that the ordinates stand off at 90 degrees to the axis. The lattice rectum is at 90 degrees. The double and single ordinates are at 90 degrees there, and the directrix is 90 degrees. That's the terminology associated with the 2D side. We'll be taking this much further in time to come, but for now that's just the a lot of the common terminology and the derivations of where these points and lines come from. That's it for this video. Thanks for watching.